Good morning. So let's quickly recall what we have done so far. We looked at the charge. Charge is a property of a massive body to cause an electric field in the planar. An electric field itself is a quality of the planar. So if I look at a charge, for example, right here at Q, we compared it to a faucet because this charge is sort of pumping electric field into the space around it, into the planar around it. So because this is pumping electric field or maintaining that electric field around it in the planar caused by the charged body, we compared, we made a lot of comparisons between flux and the field with respect to incompressible fluids. In fact, we have derived the Gauss's theorem while discussing the fundamental definition of divergence. To quickly recall what we did there in terms of fundamental definition of divergence, if you take any surface, if I take a potato, right, for example, and so this is three-dimensional in general. If I want to find out what is the surface integral of any vector, let's say j dot dA over the surface, then we had seen that we can chop the surface into sort of this potato into potato chips, tiny potato chips, and we can label these different chips as I. So I can cut this down into several chips, label this as I, so then I can write this as sigma of I is equal to 1 to n. So I'm breaking it into n pieces, right? I'm breaking it into n pieces. And this I is the index that runs from 1 to n pieces. So I'm getting this integral over each surface. Notice that this is SI over each surface, and then simply adding it up. To get the overall flux on the surface itself. So this entire thing, this entire outer boundary is the surface S. Because if I divide the pieces to be very small, that is, if we have delta V going to 0, to avoid each term itself going to 0, we rewrote this as the overall surface integral of j dot dA. We wrote it as I is equal to 1 n and SI j dot dA. So if I chop these into tiny pieces, for example, if I chop this into tiny pieces, and the volume of each piece itself is going to 0, then it is so tiny that this may go to 0, and you may just get sum of zeros. So to avoid that, what we do to avoid the proportionality effect, we divide by delta V and multiply delta V, and take that in the limit delta V goes to 0. And we have seen that this is essentially combining these two, limit delta V goes to 0, the integral j dot dA divided by delta V was the fundamental definition of divergence that we had seen. So then, in case delta V is going to 0, the number of pieces goes to infinity. So then this summation would become an integral. So this would give us integral of del dot j dV. So this is what we had seen from Gauss's theorem. If you don't recall it, please go back to the detailed discussion in the previous lecture on chapter 1. So we're going to make use of this for electric fields particularly now. So if I have electric field, electric field of a point charge, electric field of a point charge could be written as kq by r square along r. And we do know that we can express any continuous charge distribution as a superposition of multiple point charges. That is, if I have some charge distribution here, right, I can go to each point. I can divide this into tiny cells, and I could go to each point and pick this as a point charge and calculate the field at any point P due to this, and just sum over all the parts in this charge distribution. So ultimately, I can just use the point charge to get the electric field from any continuous charge distribution. So now, if you look at this electric field here from a point charge, you can see that it is spherically symmetric, right? Because it's going out. If I have a charge here, it's going out radially, and it is decreasing as 1 over r square, but that's happening overall at any direction, right? So it's spherically symmetric. It doesn't depend upon theta or phi. So because it is spherically symmetric, you can see that if you integrate this over a sphere, you should just get a constant value. Or in other words, what we are saying is, if there is a faucet here that's spreading out water, like how the charge is pumping electric field, then if I take the flux of water flowing through this area, then that should be proportional to how much water the faucet is putting out or pumping out. So then we can take the surface integral of E dot dA, and we have spherical coordinates, right? So in terms of spherical coordinates, I have over the surface, I would have the dA element. So if I take, let me show you how the dA element looks like here. So let me get rid of this. And so if I take a point charge, and so I have some charge here, and I have some surface S which is spherical, and I'm choosing a spherical surface because the electric field is inherently spherically symmetric. So if I take some point here, some small area, right, at R, so I'm looking at the small area, that small area would be R times d theta times R sine theta d phi. These are the R sine theta and R are the scale factors, like we have seen for spherical coordinates. So the area element here would be E times R d theta, R sine theta d phi. So that would give us E is simply kq by r square, and this R and R multiply to give us another R square. Then we would have sine theta d theta d phi. And this r square cancels out, and this sine theta d theta d phi, when you integrate it over the surface of the sphere, essentially they give you 4 pi, the total solid angle. And so we would get 4 pi kq. So the total surface integral of E dot dA is 4 pi kq. Or in other words, what we are saying is what is coming out of the surface depends upon what is pumping it out, the strength of it. So that's what we get from simple integration. But then we can go back to Gauss's theorem, where we know how to connect surface integral to volume integral from the fundamental definition of divergence. So then we can take this surface integral. We have surface integral of E dot dA is equal to 4 pi kq. But from the fundamental definition of divergence, this should be equal to the volume integral of divergence of E over a volume V. So if I look at this 4 pi kq, then I can write, if I have a charge distribution, I can write 4 pi k. Instead of writing total q, I could write it as rho of r over dv. So I'm integrating for the entire charge distribution to get the total charge. So this would be equal to volume of del dot E dv. By comparison, you can see that del dot E, the divergence of E, should be 4 pi k times rho. Right? And in SI units, k is equal to 1 by 4 pi epsilon naught. So if I plug that in, I would have 1 over 4 pi epsilon naught times rho. These cancel out, so I have rho by epsilon naught. So this is Gauss's law, not to be confused with Gauss's theorem. And this is very useful in solving problems because based on the symmetry of the charge distribution we have, we could choose a surface so that we can make this surface integral very easy, right? So we could find what this del dot E should be, and from there we can find out what the electric field should be. Instead of doing the traditional integration with Coulomb's law, we could instead use this to find out the electric field. But that is only for the statics case. So we're not talking about any movement or the motion of charge itself. So one has to be careful there. So then I can write divergence of E I can write divergence of E as 4 pi, sorry, rho by epsilon naught. So that's Gauss's law, and it's going to be the first Maxwell equation that we looked at. Now let's look at another thing in terms of E. We saw that E is spherically symmetric. What does this lead to in the static case? Recall that if I take a line element in spherical polar coordinates, if I take a line element dl in spherical polar coordinates, that looks like dr along r plus r d theta along theta plus r sine theta d phi along phi. So if I want to take line integral of electric field going from point A to point B, I can do that. I know that the electric field is kq by r square, r, and the dl is this, so I have drr plus r d theta plus r sine theta d phi phi. So then that gives me kq by r square. Only r dot r survives, so I have dr, right? So then I have minus kq by r between points A and B, right? So then I would have minus kq 1 over rb minus 1 over ra, or I can rewrite that as kq 1 over ra minus 1 over rb. Now this is for going from say in three-dimensional space. We are going from let's say from point A, let's say here, to point B here. So it's going this way, let's say. Now what happens if you complete the loop? So instead of taking this as the line integral, so if you take instead of taking the line integral, what if you take it as a loop? So for example, let's say it's going from A to B and then going back to A. Then you can see that if I'm going from A to B and B to A, from B to A it's exactly opposite of this. So if I have the total integral of E dot dl instead of the line integral, note that there is no closed loop here, so I'm just going from A to B. But if I have a closed loop coming back from B to A, on my way back it would be exactly the opposite of this. So overall these two will cancel out, and that happens in general for anything because we can divide any loop into small segments that would look like this, as we have discussed in Stokes' theorem. So these two segments cancel out and these two segments cancel out, right? So E dot dl over a loop is essentially 0. So this means that then we can define a potential that that describes the electric field better, because we can write this electric field itself as a gradient of some function, and we call this function as potential. So the first thing that you have to note here is that because of the very nature of the electric field, like how we have seen, because of this, the very nature of the electric field, that if you go around a loop, the loop integral is 0. So then we can use this to write the electric field as gradient of phi. If you remember from homework 2, you showed that curl of a gradient is 0. So you showed that curl of a gradient was 0. This was one of the homework problems in homework 2. So now why this becomes important is because of the Stokes theorem. So if you recall, we did the Stokes theorem right after Gauss's theorem in chapter 1, and in case of Stokes theorem, we were looking at the curl, and just like the case of divergence, we got a relationship between the integrals, right? So if I go around a path, right, and do j dot dx, right, then that is equal to surface defined by the path, right, curl of j dot dA, where the sign of dA depends upon the way you traverse, the way you go around on the surface. So for example, if I have some loop here, right, so then I can take the surface enclosed by this loop. So the loop integral, this itself is talking about the outer loop, and this is talking about the areal integral that is covered by this loop. We have done this in great detail in chapter 1. This is the Stokes theorem, right? So if I have the closed loop integral to be 0, then that means the curl itself is 0. So I can write from what we have seen here, I can write that curl of E should be 0 from Stokes theorem, and based on that, based on this curl of E is equal to 0, then you can see how electric field may have a potential. It is not coming in because curl of E is equal to 0, but rather it's not just a mathematical convenience, but we can think a little more deeply about what this potential means in the next few slides. So here you can see that if I define electric field as a gradient of potential, then you can see that gives you this nice equation here. But what does this potential mean? Is it just some scalar function that is there for mathematical convenience, or it is deeper? So unfortunately, to understand that, we'll have to go deeper into gauge transformations and other quantum effects. But this potential is also a quality of the planar. It is not just some random number that you're picking, but it is indeed a quality of the planar. So what do we mean by that? Is that, for example, imagine if I have some charged slab over here at this end. So let's say this is charged. Then there is electric field because of this in the planar surrounding it. So I can divide, let's say, the planar that is here. I can divide this into several boxes, right? So when we talk about electric field, we talk about a magnitude and a direction. So if we want to talk about the direction, we need two cells, right? We need the nearest neighbors because we want to point in the direction in which the electric field is changing. We need at least two cells. And ultimately, what we want to study is if I bring a charge here, if I bring some charge Q here, how much impetus or momentum this charge is going to get because of the electric field produced by the slab. In ultimately what we want to write is the force equation. F is equal to QE. So the electric field is how much impetus is caused in this charge by the electric field present around it. So this electric field itself doesn't give you any idea of energy directly. So, but this phi gives you some idea of what this how much energy the field around it can cause in a test charge like this. And if you compare phi from two cells, the gradient of it can give you the electric field. So what I'm saying is if you have a slab, you can divide the plan around it into cells like this, and you can assign each cell a number. So this is the closest, so I can assign this number 1. These are a little farther, so 2, 3, right, 4. And I'm able to assign these numbers because the charge that is here is changing the plan around it because it acts as a source for the electric field, right? So if I do like this, then I can see that the potential here is not the same as here. That means there is some change. That means the change between these two cells is giving me the direction of the electric field, that it is going this way. So so that's why we really call potential as a quality of the plana itself, and it will be justified more when we talk about electrodynamics, why it is a real quality of the plana that will require a discussion on gauge constraints in full electrodynamics, which we will talk about later. But for now,